So let's go over problem 4, mission impossible. Let's remember that for any two vectors u and v, we know that the dot product between u and v is equal to the magnitude of u times the magnitude of v times cosine theta. And then we're given the fact that the dot product between u and v is equal to the magnitude of u times the magnitude of v. And this tells us that cosine theta is equal to 1, or cosine theta is equal to -1, which means that the angle between u and v is 0 degrees or 180 degrees. And this means that u and v are scalar multiples of each other. And this tells us that they may point in the same or opposite directions. So let's use that logic to check these statements. So u and v in the same or opposite directions. So the first statement is done for us as an example already. So starting with statement 2, u and v are orthogonal. Remember that orthogonal means that the two vectors are at a 90-degree angle. We just proved that the angle is either 0 degrees or 180 degrees. And since the vectors are non-zero, this is impossible. For the third statement, the magnitude of u minus v equals 0. This happens only if u and v are the exact same vector. So if u equals v, this would be true. While they are scalar multiples, they don't have to be the same length. So for this statement, it's possible but not guaranteed. For the fourth statement, u and v span a one-dimensional subspace. Since one vector is just a multiple of the other, they both live on the same line through the origin. So u and v live same line through the origin. And that is the definition of a 1D subspace. So def of 1D subspace. So this is guaranteed. For the fifth statement, u and v span a two-dimensional subspace. To span a 2D plane, you'll need two vectors pointing in different directions. And since these u and v vectors are scalar multiples, they can't spread out to fill a plane. So this is impossible. And this is because u and v are scalar multiples. All right, for the last statement, the magnitude of u plus v is equal to the magnitude of u plus the magnitude of v. This equality only holds if they point in the same direction. And that is when theta equals 0. If they point in opposite directions, the length would subtract. Since both cases are allowed by our original equation, then this is possible. Okay, so now for the second part of problem 4, we're given 3 pieces of information. Z are unit vectors, and then the distance between them is also equal to 1. Think of this as an equilateral triangle in space. So we want to find the magnitude of w plus z. And the trick here is to use the relationship between the magnitude squared and the dot product. So first, let's find the dot product and expand the information we do have. So using the magnitude of the difference squared, we can write this as w minus z dotted with w minus z. And if we FOIL this out, we'll get w dot w which is the magnitude of w squared minus 2 w dot z plus z minus z dot minus z, which is equal to the magnitude of z squared. And notice that this is equal to 1 squared from our given. So now let's substitute our known lengths of 1. So the magnitude of w squared is 1 squared minus 2 times w dot z plus 1 squared is equal to 1 squared. And let's reduce this down so we get 1 minus, just do 2 minus 2 times w dot z is equal to 1. And then now let's isolate the dot product. We'll get 2. Let's pull this 2 out. One minus w dot z is equal to 1/2. And then we can see that the dot product is equal to 1/2. Now that we've used the dot product to find the magnitude of the sum, we can start by squaring it. So w plus z squared. Since we're trying to look for the sum, the magnitude of the sum, we can expand this out like we did above. We'll get the magnitude of w squared plus 2 times w dot z plus z squared. So our magnitude is z squared. And plug in our values of 1 for the unit magnitudes and 1/2 for the dot product that we found up above. We get 1 squared plus 2 times 1/2 plus 1 squared. Get 1 plus 1 plus 1 equals 3. And to get the final answer, we'll just take the square root of both sides. And we can see that the magnitude of w plus z is equal to square root of 3.